Welcome to Spring LIB.
All right, so for this problem, we are dropping this super dense cube onto the surface of the Earth. And normally, we can ignore the motion of the Earth because the objects that we drop are much, much smaller than the Earth. But in this case, it is half the mass of the Earth, so we need to account for the motion that the Earth will have as well, as it will be pulled towards this mass, even as the mass is falling towards the Earth. So some of our change in potential energy, change in potential gravitational energy is going to be used by the Earth as it moves toward our mass. So we need to take that into account. So we are just going to start. I'm going to write this mass here as m over 2, where m is the mass of the Earth. So we're just going to say that m over 2 times g times h is the starting position of this mass, and then the change in potential energy is as it drops from h to h over 2. So the change in that height is actually h over 2. So this is the change in gravitational potential energy. And I can get away with using little g here because we were told that h is much, much less than the radius of the Earth. So we can go through using the true gravitational form, but we'll end up with the exact same answer because we'll end up ignoring that when we get to it. So I'm just using little g here at the outset. So bear that in mind. So this is the change in potential energy as these things are being pulled together, and that's going to be equal to the change in kinetic energy of both our mass, so 1/2 m over 2 times its velocity squared, plus the change in kinetic energy of the Earth, which I'm writing its mass is just m, times its velocity squared, and we'll call that VE squared. So this is our conservation of energy equation. The change in momentums will also be conserved. So we'll have the change in momentum of our object, which is going to be m over 2 times its velocity, and the change in momentum of the Earth, which is going to be m times its velocity. And if we solve this for the velocity of the Earth, we're going to get mv over 2 divided by m, so just v over 2. Then we're going to plug this into our conservation of energy equation right there. And if we rewrite this, let's go ahead and get rid of some of these 1/2. So let's multiply everything by 4. That'll take care of these two, this one, and put a 2 in front of that. So now we're going to have mgh. Let's make that explicit. So we multiplied everything by 4. So now over here we have mgh, and that's going to equal mv squared plus 2 times m times v over 2 squared. So that's going to be m times v squared over 4, and then this 2 will cancel out cancel the 4 into a 2. So now we are left with this equation here, where all of these m's are the mass of the Earth, these v's are the velocity of our object as it's falling. So now we can factor out a v squared. So let's do that right here. So we factor out our v squared and then divide both sides by this term here. Let's actually change this. It's going to be a 2m2 over 2. So we're going to multiply through by 2. We're going to 2 mgh over here on this side divided by, we can factor an m out of there as well. We're going to cancel this m. and then we'll have 2 plus 1, or 3 down here at the bottom. And that's going to equal v squared. And then if we take the square root, we're going to get v is equal to the square root of 2gh over 3.